So let x1, x2 and so on, xn or n random variables. So these are said to be jointly Gaussian. If the joint PDF of these random variables is given by fx1, x2, so on, xn, or x1, x2 and so on. What this indicates? This is a joint PDF. See, in case of two random variables, we are writing fxy of x comma y, but we have n random variables, x1, x2, so on, xn. What is this small x1? Is the value that taken by the random variable x1. x2 is the value that taken by the random variable x2. So this is extended to n random variables. This must be equivalent to Cx inverse. So determinant of Cx inverse power 1 by 2 divided by 1 by 2 power n. See, in case of two random variables, we have 1 divided by under root sigma x, sigma y into 1 minus rho square. So this is for n random variables. Later I will explain what is that Cx into e power minus 1 by 2 times x minus mx into t, and this is Cx into x minus my, sorry, mx. This t indicates the transpose. So this should be the joint probability density function of these random variables x1, x2, so on, xn. Then only we can say that the corresponding random variables are jointly Gaussian. So here this x minus mx is a column matrix. See, this indicates matrix, something inside. That is, if you write something here, the meaning of this is a matrix. Is a column matrix that is represented as x1 minus mx1, x2 minus mx2 and so on. Xn is capital N, we use a capital N, minus mx. Understood this? That is, this x minus mx is a matrix, is a column matrix, which is x1 minus mx1, x2 minus mx2 and so on, xn minus mx. Follow? Actually, instead of writing this column matrix, we are denoting this like this and we are writing here, okay? Just for simplicity. And this x minus mx t indicates the transpose of this matrix. That is x minus mx t is the transpose matrix, a transpose of x minus x. And this Cx is called as the covariance matrix. The Cx this is equivalent to C11, C12 and so on, C1n, and this is C21, C22 and so on, C2n, and this is Cn1, Cn2, finally Cnn. So this is called the covariance matrix. Here x minus mx, cx, both are matrix. X minus mx is a column matrix that is represented by this, and cx is called as a covariance matrix, where this Cij is represented as is equivalent to expectation of xi minus mxi into xj minus mxj. See, expectation of x minus mx into y minus my is the covariance of x and y, is it? Expectation of x minus mx into y minus my is called the covariance of the two random variables. So in the same manner, this is the covariance of the random variables xi and xj. For the Cij values, that is C11. C11 is equivalent to expectation of x1 minus mx1 into x1 minus mx. Similarly, C12, C21 and so on, Cnn. So if you know this equation, we can find all the Cij values. Substitute these Cij values in the covariance matrix. Then take that covariance matrix and substitute in the expression of the joint probability density. Here you can write this Cij is equivalent to expectation of xi minus mxi whole square when I equivalent to j. Is it right? When I equivalent to j, the Cij is equivalent to expectation of x minus mxi whole square. What this indicates? This is the variance of xi, is it? Expectation of x minus mx whole square is the variance of x. The expectation of xi minus mxi whole square is the variance of xi. So this can be represented as expectation of that sigma xi whole square. So for simplicity, we are writing it as sigma I square. That is, the variance of x1 is sigma 1 square, variance of x2 is sigma 2 square, variance of xn is sigma n square. Follow? So this Cij is equivalent to expectation of xi minus mxi multiplied with xj minus mxj when I not equivalent to j. So what we call this? When I not equivalent to j, see, when I equivalent to j, we call it as the variance. This is the variance of the random variable xi. See, if I is not equivalent to j, then we call it as the covariance of xi and x. So how we represented covariance? sigma xi xj. So for simplicity, I write it as sigma ij. So sigma ij is the covariance of the random variable xi and xj. See, when I equivalent to z, it is becoming the variance of the corresponding random variable. When I not equivalent to j, it is the covariance. Then, can we write the Cx now? The matrix Cx is equivalent to, what is C11? C11 is the sigma 1 square, C12 sigma 1 2 and so on, C1n sigma 1n. This is sigma 2 1 sigma 2 square, sigma 2 2, that is C22 is the sigma 2 square and so on. This is sigma 2n. Similarly, this is sigma n1, sigma n2. Finally, we have sigma s. Now, can you see if x1, x2 and so on xn are given, we can evaluate the Cx. Is it? We can easily find the Cx value. So, once you know Cx, can we find the inverse of this? What the Cx inverse indicates? Here, Cx inverse. Cx is the covariance matrix and Cx inverse indicates the inverse of this matrix. Okay. This is the inverse matrix. So you can evaluate the determinant, you can find the inverse of it. Similarly, once you know the inverse matrix, so what this indicates? It's a determinant. First find the Cx matrix, find the inverse of that Cx matrix, then find the determinant of it. You substitute that determinant value here, and similarly this is a constant. You know this value. Now can you find if the x1 is given and the corresponding probability density function is known, you can find the mean value of x1. We can find the mean value of x2 and so on, mean value of x3. Therefore, we can get this matrix. So all the random variables are given and the corresponding the probability density functions are known to us. We can evaluate all these quantities. So once you know these values, we can substitute those values here and we can find the joint probability density function of n random variables. So the joint probability density function of these n random variables is equivalent to that much. Then the random variables are said to be jointly Gaussian random variables. See, first we considered the two random variable case, two jointly Gaussian random variables x and y. Now we extended that to n random variables. These x1, x2, so on, xn are said to be n jointly Gaussian random variables. So they are said to be jointly Gaussian when the probability density function, that is the joint PDF of these n random variables is given by this much. Is it clear to you?